Hi, good afternoon. This is Hongbo. Uh, I'm working for KT as a research engineer of infra laboratory. Um, Today, I'd like to share a small experience we KT went through while we actually struggling at the beginning stage of machine learning technologies into um, adapting this technology into the network operation area, mostly network operations and management area. So um, at the next slide, next page, uh, the order of my talk will goes like this. Will go like this. The first I'll I'll present some. Oh, thank you. I can. Uh, I'll talk about the future of the network operations, how the phases will proceed roughly. And secondly, I'll talk about the what kind of machine learning technologies need to be considered to accomplish those evolution. And thirdly, I'll share three examples of our struggling. And lastly, I'll put some interesting consideration points. So let's look at the current situation of network operations, operational environments. So typically, as you can see on the picture, uh, left-hand topmost picture, I drew the IP or wireless domain management area. It's let's say we have a different domain of networks as a telecommunication service provider. So there are different domains, IP domains or wireless network domains or transport domains or cable domains or even field dispatching domains. So we allocate a team for each domain, right? So a team will consist of 10 or 20 people for a local area. So in global, it should be a couple of hundred people will work together for covering each domain. So, uh, so in this situation, if there's some problem happen, then the team members should share the situation, and they need to discuss about what's happening in their domain and to resolve the problem. Um, because the reason why they need to talk about is typically each person, each team member, uh, actually is monitoring and operating their segment. For example, when you think about wireless network, uh, if one guy will be taking care of frontal, and the next guy will take care of uh, backhaul, and the third guy will take care of wireless core network. So if something happened, then a lot of alarms and warnings just sprung out of their terminal. So at the moment, it's very hard for them to figure out what exactly happening. So they need to discuss. They typically they spend more than 20 minutes to figure out what's happening in their network. So if uh, those kind of problems are exist, uh, those kind of problems exist in this situation. So to improve this situation, we started to integrate vertically and horizontally first and vertically. So when you look at the phase one picture, we squeeze the tip. Okay, the different systems for different segments is aggregated into a single system in each intradomain. And we now you see in on the picture only one single type of machine is taking care of whole domain. Actually, KT has been developing a integrated management system for IP domain, and it's almost successfully done. But wireless domain, we were still uh, experiencing hard time. Uh, and the transport domain, it's ongoing. It's going to be completed in a couple of years. Cable domain, we just started to establish we just started to develop a next generation type of OSP management system. So all of the systems for each domain uh, are being have been being integrated intra level at the intra level, and in the second phase, uh, we're gonna we're gonna merge them into the vertically into vertical integration would be uh, we're going to try to integrate those systems vertically so that they're they're monitor and operate whole 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 networks uh, as a single one. So I forgot to mention about the concept of end-to-end management. In this picture, we can monitor and operate end-to-end network elements intra-domain scope. And so in phase three, we're going to integrate the systems vertically so that any operating members can monitor and tell what's going on in any place in the whole networks. So in future, uh, in the final stage, we're going to build up a humanless control center. So this will be the final picture of our control center. There's no human being working inside the control center. Only the AI system will cover all the problems, and issuing trouble tickets or kind of various operations will be conducted by AI. And and even the outside, we're going to put robots. Robot engineers will visit your house to fix the outside problems. So that's going to be the final picture. But I don't know when we can accomplish this goals. Let's look at the what kind of technology is needed to make this transition happen. So the during the first transition, we have put more focus on these three items: big data technology, and event correlation technology, and fault localization technologies. The big data, because as I mentioned before, we in phase one we did implemented end-to-end monitoring system. So a lot of data need to be well organized and well prepared for the analysis. So and beside that the timetable time schedule was well met with our transition process, because big data is has been very hot several years ago, and at the moment we did started to integrate IP domain network management system integrated, and mm, and event correlation, and also uh, because we integrated all the segments, network segments, so it was very hard to to correlate the events and alarms. So event correlation technologies was a kind of traditional subject in this area, network management area. So we can easily adapt that concept into the integration work, integration task. And fault localization, because we need because since we integrated these segments uh, in order to figure out what what location, what position made such a problem, we need to this technology, port localization technology. So there are tons of other technologies there, but we KT uh, put more focus on these three areas. And the next transition, um, in the second transition, our focus laid on to the automatic provisioning and intelligent analysis and fault prediction. So as for uh, automatic provisioning, we're going to transfer to the phase two based on mostly based on SDN technology and SON technology. These are the core technologies to accomplish this transition happen. So as for the automatic provisioning, uh, so the automatic provisioning is mostly can be accomplished by adapting SDN technology. We built up a lot of SDN controllers for each domain, each layer, and in the one of the major roles of SDN controllers is being used as a method to provide the provisioning, the service provisioning. So, and the intelligent analysis, because this kind of cross-domain environment, cross-domain situation, the analysis is very much complicated. So uh, so we need intelligent analysis way method. And as for the fault prediction, uh, because the configuration will be getting complicated, so we want which part will cause some kind of problems before it happens. So again, not only these three technologies needed to make this transition, but this is the case of KT's experience. So we did put more focus on these three items. And in the future, actually right now we're most of our members working on these three parts. So operations should be learn by itself, and we need uh, we need intelligent before service. Before service means if something getting bad or something worse, then before something happen, we will do some kind of activities to prevent them. And traffic forecasting is an interesting area where we I'll talk about it later. So, so this is the first item that I'd like to share regarding the KT experience. Um, uh, we, I I totally agree with Dr. Jacob in the previous session. It's very hard to apply those brand new technologies into the data because lack of data. We don't have much very nice shaped data, but uh, at, as a researcher, we at least we have to try something. So we focus on the travel ticket, and travel ticket is issued to the field members, and but the problem is the travel ticket sometimes need to somebody go to the field, but sometimes it just can be covered in the office by remotely connecting to the system, or even sometimes travel ticket just lets the operators know something. It's an informational travel ticket. So we started to classify travel tickets to figure out, is this really we need to send out somebody to the field, or is this just we can cover it inside? So this this classification neural net model is very simple and very basic, but we the, the result of this application was not bad. Actually, as you can see, it's very easy to accomplish the accuracy, right? You prepare the data from the travel ticket stories and put it in the CNN kind of, it's LessNet or AlexNet, anything. Put the data into the classification model, and it's going to tell you uh, one of two. It's very easy, and the accuracy will go up to 95% something. Human operator working for KT only can tell uh, 85%, so it's 10% more accurate. And next item is uh, mm, basically it's traffic prediction, traffic forecasting, but to uh, prevent the abnormality. Uh, we used LSTM-based autoencoder type of model, and luckily we've already maintaining a gathering information gathering system. It's tapping between the MME and HSS and S gateway, between the S gateway, P gateway, and between MME and S gateway. They are collecting all the serial data, and so we've already had a lot of big size of data, and we extract 1 minute 1 minute units data and put it in the LSTM based autoencoder model, and we can figure out, is it going well or going bad by measuring the gap, the Euclidean distance between the trained one and the predicted one. And next item is we built up a common AI platform. So the engineers in the field, most of them are maintaining their own Excel spreadsheet um, to handle their customers or their specific equipment. So they can use this common platform. They can easily build up their own AI application, and then put their data into that created application. Then it's gonna, for example, in this picture, you put some customers data into the created application, and it's going to be trained, and after that you put a new item, 8252 Robinson. Then it's going to tell you, hey, that customer can make some trouble. He always making trouble. Those kind of information can be extracted. So while we're struggling at the beginning stage, we realize that some kind of standardization items can be provided then to help us. So the first item is categorization of machine learning technologies for network domains and phases. And so different MLs for different domains, and requirements for training data. So minimum size, how much we need to prepare for the training, so what kind of characteristics of the distribution needed, those kind of things. Cautions and limitations, guidelines for data normalization, guidelines for hyperparameters. So right hand side, this is the picture of the future control center. It's not comfort to me. It's not convenient, and it's not comfortable to me. So next picture, again, right hand side, you call to the service provider because your internet connection has been wrong. Something happened in your connection, then somebody visited your house and opened the window, and a robot visited you. Then it's not very comfortable. Somebody can feel comfortable, but not me. So anyway, please be prepared to welcome this robot, and so this focus group is very nice. So we can think about all kind of various matters and problems and everything. So thank you for listening.
Thank you. Any questions? Yes.
Thank you very much for this precise presentation on the operations management. I would like just to understand how what you have been doing, and also the guideline you are suggesting for standardization is linked to the HCISG ANI, which stands for let me tell you, experiential network intelligence, and which aims also to use AI for network operation management. So if you have knowledge about that.
No.
Yeah.
I don't have any knowledge.
Yeah, because there is already this initiative within HC, what they call
ETSI.
ETSI.
Yeah.
Industry specification groups. So this is kind of pre-standardization activity, and it plays the same role like here, focus group. So it's good for this focus group once established to make a link with this HCISG and to
right. Yeah. Thank you.
Any other questions? Yes.
Thank you very much. I am the advisor for ITUT Study Group 2, which on operational aspect. So thank you very much for this excellent presentation on the intelligent operation and maintenance of the network. And actually now in ITUT Study Group 2, we have, I think, 2 projects on this aspect. And one of them is a framework of smart operation management and maintenance. So actually it's relevant to the potential changes to the existing framework of operation management and maintenance. Thank you again for the presentation.
Okay, thank you. It's just the information, all right. So, not, but as Dr. Jacob mentioned at the previous session, it's very hard to find out the exact matching between the machine learning technologies which is applied to a specific field. So network operational field, in my opinion, is very well met with it for this purpose, because we don't need very accurate, like it doesn't require 99.99999% of accuracy. We don't need to accomplish that much of accuracy. So this field is very good field actually. And if SG2 is you said it's already started to do so, and so then we can collaborate each other. This is just focus group, so we're going to study anyway.
Thank you. Let's thank the speaker again. So our next talk will be given by Salih Ergut.
Hello, everybody. My name is Salih Ergut. I am from mobile operator Turkcell in Turkey, part of the 5G R&D team. Today, I'd like to talk about the challenges that we see at operators, and before that, I'd like to also present some of the use cases that we see currently and see as very potential. Just a brief overview of Turkcell. We are the leading mobile operator in Turkey with more than 33 million subscribers and 45% of the market. Listed both on New York Stock Exchange and Istanbul Stock Exchange. We have presence over 9 countries with more than 50 million subscribers. We also have an R&D team, about 1,000 R&D personnel, and 5G R&D is part of that team as well. As many mobile operators try to shy away from being just dumb pipe providers, so they are trying to tap into new business opportunities. And in Turkcell, we have a vision to become the digital operator, and we are doing many things, and I think we are getting close to our targets. In addition to providing traditional services, voice data services, we provide IPTV, messaging services, like music services and etc. Also, we see the fintech type of applications as a new area. We have digital-only services, so we don't provide any circuit switch voice calls or SMS. Everything is provided over digital services with data caps closing to 60 gigabytes. And we see energy as another area that we can have a differentiation. And Turkcell is part of a joint venture in Turkey of 5 companies to produce Turkey's first car, which is going to be electric car. So we are going to be active in the automotive sector as well. So I think we've heard a lot of interesting use cases, especially in the telecom domain. So for mobile operators, I see that some of the use cases are related to marketing people, such as the churn prediction or customer segmentation, or for salespeople to upsell new products or services. So predicting the next best action for customer. This type of applications are widely used in many operators and in Turkcell as well. And there are like many established companies that work in this domain. But the network-related actually use cases are becoming also popular, and I think that's something that can actually make a difference. So I'd like to go over some of these type of use cases in this talk, focusing on the ones that we are actually already working or we see possible or exciting in the very near future. Self-organizing networks are very well established, and I think it's since release 8 we have it's already in the standards. And so far they've been focusing more on optimization, like the configuration management of the network with set of rules or policies. And now we are actually moving into a more complex network where these functionalities have to be designed end-to-end in an intelligent network paradigm. Basically, new technologies are being introduced from SDN to NFV. In the radio side, we have massive MIMO, like beamforming type of technologies. So we need to extend the SON functionality from radio to transport networks and then core networks, introduce intelligence through AI, provides SON functionalities between different domains, especially with 5G. We are seeing that network slicing is becoming very popular. And we have to be proactive. So we need to predict the network conditions and then act proactively rather than reacting to changing network conditions. Another area is especially with the technologies such as SDN and NFV, the network is becoming like softwareized, and we will be actually having a very complex network. As Dr. Jacob pointed in the previous talk, like the complexity will increase like 50%. And with 5G, probably we have to invest the same number of maybe base station nodes into a city equivalent to the whole country. So we are going to see a lot of densification in the network, a lot of complexity increase in the network. So we have to, this network automation is becoming very important. HC has actually initiated an ISG, Zero Touch Network ISG, basically focusing on this, which is aiming creating an end-to-end 5G network and service management in a multi-vendor environment and automating all the tasks in that sense. And they are also considering machine learning and the standardization as a key concept to achieve this. For operators, network performance monitoring, especially in near real time, is very important. Basically, we have an information or we have KPIs and counters collected from the field, actually received to a central location and then analyzed, and then the network performance is evaluated. But this is usually with a delay, and this delay can range from hours to days. Most of the time, predicting or having a real-time actually network performance is very crucial. If you could identify anomalies on the spot, you could actually notify the relevant parties and take actions. Even you could actually predict certain performance problems and then notify your customers so they don't have to call the customer service. That is a better customer experience, and then you can also save from costs of answering all those codes. Another area is actually making sense of the network alarms. Basically, these alarms can be correlated with outside events as well. And say you have a power outage at some location in your network, then you can predict that there are going to be coverage problems, or you have some battery-powered base stations, and you can predict their duration to serve. and then take actions. So this type of things are becoming very important. So you can predict the maintenance of your items, or you can do some root cause analysis. As Dr. Samik pointed out, interpretation of these results are very important. So you have to, when you have something and you can predict something, to know what caused it and to understand what happened is important, because like the domain experts can see some patterns in these alarms, and they are very, like when they see some sort of pattern, they can say that, okay, this is going to cause this and that. But what we could help them is actually with machine learning algorithms to provide them some patterns that they haven't noticed before. And so they have to be interpretable to make sense. So what are some challenges? The main challenge is actually the framework to run these AI or machine learning algorithms on top. So basically, as was pointed out, like 80% of the whole application, ML or AI app, is actually data collection. And this is really a big problem for most of the mobile operators. Say you have a vendor coming with an ML app, and so you have to prepare certain data for that vendor specifically. You have to provide the description of parameters, and these are usually depend on the vendor implementation. And in your network, you have multiple vendors. So one vendor's KPIs or counters and etc. are different from others. And then you have to take care of like the security aspects, letting them access to your network. The ownership of the data is also is complicated and needs to be handled. And this vendor creates his solution after too much actually effort from his side and from the operator's side, and then goes to another operator and has to repeat everything. And for the operators also, like when they have multiple vendors, it's very difficult to try them all. Like, I mean, so they have to provide certain information for them and then compare them. And this is also difficult for internal applications that are developed. So you have to go through this type of thing. So it's very critical, like to have certain maybe protocols or APIs standardized, or like the logging formats. Most of the times these logs are used for debugging your network, seeing the performance of your network. But now we are in a stage where these logs are going to be used to decide on the performance, creating the maybe optimizing your network, creating new business opportunities in your network. Most of the apps actually rely on this type of information. So here we have massive data collected through probes across the network. And when you enable these logs or traces on a user level, then they become really difficult to handle, both the storage-wise, the additional performance that, or the CPU load that they create, and then transferring all this data to a central location. So we will see even more problem as the 5G becomes widespread with the densification that we are going to be observing. So as I pointed out earlier, different vendors has different log formats. So there are certain, type of logs that are actually standardized or recommended in the standards. But mainly we have like the vendor-specific experts at operators. So we have to kind of unify this information. And also like the collecting data from different parts and then doing data fusion on top of them are also very critical. We actually even need to be able to use external data. So when you do some prediction of the mobility within network, social media can help you, or the weather information can help you. So we need to be able to use these internal and external sources when we are creating our models. And to analyze everything in the core network or at a central location is actually waste of resources. One, it introduces delay in the analysis, and second, it creates additional traffic on the backhaul that you could have used for user traffic. So it is important to have sort of like distributed analysis, local analysis, and then not maybe you can create like the summaries of data to be collected centrally. So on your edge network, you can do some algorithms, run some algorithms, do summarizations, and like anomaly and this type of information can be fed into the overall network. And with the new architecture, 5G architecture, we will have edge computing. So this will be available for us. And the network orchestration is an important aspect that needs to be handled. We will have a very flexible network, but then it's going to be very complex. So we will have actually network functions across our network that are trying to optimize different goals and changing the same parameters. So we need to have orchestration as opposed to network management. So we need to be able to do this orchestration among these functions. So as I said, in a multi-vendor environment, it's important to define the foundation of the AI. As a summary, I'd like to focus that actually we will be seeing more and more use cases for telecom operators. These will be ranging at different layers, and I mean we will see this. And to make it, I mean, move faster, we need to have the foundations ready, and I think this is a good step forward. Thank you.
Thank you. So do we have questions? Yes.
Hi, this is Jakob from Nokia. I don't really have a question. I just think this is a great presentation, and I just think that gave possibly many, I think, really good directions to what this focus group could be about. And I think no one has mentioned this multi-vendor aspects of harmonizing APIs to get data. I think this is really, for me, this is really the foundational problem. If you don't have this, I think it would kind of jeopardize the whole idea. I think this is really key. And I also like the aspect of, avoiding that multiple algorithms touch the same parameters with different goals in mind. This is also something I haven't seen, and especially when people look at, I have a machine learning algorithm that optimizes X. And then you're not in an isolated universe, but you want to do this coexist with many different algorithms. So I think this is a key aspect, and I haven't seen this in any academic literature so far. People mainly focus on one specific problem that they're trying to solve. I have never seen any multi-machine learning algorithms that operate at the same time. So I think this might be a really good topic also for the more, say, academic. This might be a point where academic research is not currently focusing on. Good. So just comments on your presentation. So thank you.
Other questions, comments?
Maybe. Is this not related to this topic of federative neural networks? What you just mentioned?
Is this related?
I mean, this team deep neural networks of federative. What Marwan was talking about, also David.
Maybe they should comment. I had the feeling that there was like you have multiple agents that work towards a common goal, but they essentially want to maximize or optimize the same metric. But I get the feeling from your talk that you might have multiple algorithms that would like to solve for different things, and they are not working on an isolated system anymore. These algorithms need to coexist. So maybe I think this is different.
Maybe a simple, maybe an example would be like not thinking, like say you try to extend your coverage, and then you have an interference management agent. So like both of them are actually doing some different optimizations in their network. So when you run this type of different functions, you will have to coordinate them. So if you just let the interference management, then that's going to shrink the network to a very small size, and you will have to trade off your, say, capacity. So this is a simple example, and then there are actually many aspects. As the network is more complex, you will have like different optimization network functions doing some optimizations, and they have to be in coordination with others. Otherwise, I mean, you can have improved like some parameter, but then you will suffer on the other performance metric.
Okay. Yes.
Well, I think that the interesting things in this presentation, beyond the fact that it was very clear about the problems in the telecom, it's lists a lot of problems that are more generic to the big data and AI than just the telecom. And this is why I think that it is important for this focus group to link with other standardization activities. So when I see here you are talking about reference architecture, data format, it refers me directly to an activity ongoing in ISO IEC Joint Technical Committee 1. There is a working group 9 on big data. And the first thing they have started to do is to build or to set up a reference architecture for big data. And we can find all these problems expressed in different ways. Having what we call also in situ analytics, bringing the analytics to locally to do the analysis and bring the insight. The problems of privacy of data, this is a big problem in the telecom. I think this is something that telecom industry has to deal with it, and this is we can discuss longer about that. So my main point is that we have to learn also from what's ongoing elsewhere with a good example, this working group under JTC1.
Yes, the final question.
Okay, this is not a question, but a comment. And if you mention about the JTC1, they established a new study, new subcommittee, SC42, that is artificial intelligence. And its first meeting will be held in April 19th or something. Then they discuss the framework of AI. And there is an ongoing activity in IEEE that I have submitted a contribution to the focus group. There, in that IEEE activity is briefly explained. So there are many standardization activities. Thank you.
Thank you. Okay, so let's move to the next talk, but before we need to thank the speaker again. The next talk will be given by Wei Meng.
Sorry. Good afternoon, everyone. First, I appreciate that I have the opportunity to share our ZT experience and ideas in this workshop. And before my presentation, I would like to share a story. In the early 19th century, there was a race between a horse carriage and a locomotive. As a point of view of today, it is really a joke if the horse win the game. But actually, but it was not the same in the early 19th century. Eventually, the horse won the game because there was a mechanical failure stopped the locomotive. So this story tells us the progress of every new technology is not a trouble-free journey. You know, the AlphaGo has defeated many famous Go players in the past years. But actually, the AI technology has met 3 big waves, and we are now standing on the 3rd one. So AI has changed a lot in our life, include network. There are 2 parts in my presentation. The first is a point of view on AI, and another is I will show you some use cases on how AI promotes smart networks. So what is AI? I think many different people have different answers. So look at the picture. It is a cat. The deep learning is responsible for auto-characteristic extraction, and machine learning is responsible for auto-rule creation. And during a successive training, the machine can recognize it is a cat, CAT cat. But not only deep learning and machine learning, in our opinion, any use of machines instead of humans to complete the work which usually requires human intelligence to complete. All of these can be considered to belong to the scope of AI. And based on the hardware such as CPU, GPU, and the algorithm, AI technology can be applied in many vertical industries, such as smart city, smart home, smart network, smart operation, and smart robot. So the big data, algorithm, and the computing power are the 3 key factors to accelerate the AI progress. So on this section, I would like to share some stories. Based on AI, machine learning, deep learning, and big data, there are 4 aspects for the AI impact on the network. They are intelligent O&M and intelligent optimization, operation, and the security. So this use case is about the AI-based intelligent network O&M. And what is O&M? O&M is network operation and maintenance. So the output of the picture, R&D lab, for example, the step 1, step 2, step 3 is the training process. For example, event A can be extracted into some features according to the history alarms. So after successive machine learning and training, the relationship between event and feature can be established. And the lower picture, this picture, is the production network. AI platform is responsible for feature matching based on the monitoring data. And these data are from the current network. And the AI platform will give the result and the analysis and decision to the implementation system. And the failure handling will be implemented into the network. So, okay, these are the challenges of today's O&M, network O&M. So using AI can perfectly solve this problem. So this is these are the advantage and benefits. Before the event, we can do health detection, alarm prediction, and smart warning. And when the event is happening, we can do the alarm control, RCA analyze, and etc. And after the event, we can do the success training according to the history alarms. So the benefits are very obvious. So this is about the intelligent network optimization, and this is an overview of the optimization solution. And the production network provides data such as MR, CDT, Carriage, and DPI from the base station and or the terminal cell phone and other network node. And these data will be provided to the big data for pre-process, and this data pre-processed data will send to the AI platform for model training and prediction. The adjustment suggestion will send to the implementation system, and this suggestion will be implemented into the production network automatically or manually. So this is an overview of the optimization solution. This is for your reference, the forecast of human cost savings. If we introduce SON technology, there will be 20% off on the human cost. If we introduce auto configuration, there might be 50% off on the human cost. If we introduce big data, there might be 70% off. If we introduce AI, there might be 90% off on the human cost. And this use case is about the intelligent carriage optimization for the 5G cost base station. These are the production data such as KPI, configuration, and this production data are connected from the base station and other network nodes, and through pre-processed by big data, AI platform use this data. AI platform will do the original training, do the model training, problem area mining, and the prediction, and then the AI platform will give a reasoning result output to the big data platform, such as this suggestion, antenna inclination suggestion, power parameter suggestion, labor suggestion, and engineer suggestion, to improve the base station coverage. And this use case is about the capacity optimization, and it is very similar with the last slide, last use case. The only differences are the production data and the action of AI platform and the suggestion. Okay, this is about the elastic 5G core network slicing strategy. After NFV deploying in the network, I think the resources will change frequently according to the network load. So AI can provide an elastic 5G core network slicing solution. Step 1 and step 2 are the training process, and the training model will be established based on the history data, and step 3 and the production data will be provided to the trained model and give a decision and implementation to the implementation system. And this blue line is the user experience, and the green line is the resource occupied. It's the forecast. So it can provide a continuous optimization solution in the 5G core network. So this is about this is the use case about the intelligent traffic prediction of barrier network, and the previous use cases are based on the single algorithm, and this use case is based on multiple algorithm for users choosing. The R&D lab step 1, step 2 is responsible for establish the algorithm library, and the production network for the production network step 1, step 2 and step 3 is for user to choose appropriate algorithm for the in the AI platform, and plus holiday correction factor and the current network data, AI platform can provide a prediction and output to the suggestion system. So this is a use case about dynamic routing optimization. Step 1, step 2 is the data collection process, and at the meanwhile the traffic forecast model and the strategy model will be provided to the AI platform. And the AI platform will give a routing optimization to the production network, and it will create a closed loop for the network. As you know, the traditional routing optimization, we always use TE technology, traffic engineering, and but if we use AI, introduce AI in the routing optimization system, it will be make the network more efficient and accurate. And this is about the intelligent operation, and this use case is mainly for the to improve the business sale. For example, people like playing a mobile game, and this data will be collected by the operators. The operator will push accurate mobile packet to the terminal user. So there are 4 steps in the use case: service creation, business sales, experience guarantee, and business optimization. This use case is about the security, attack and abnormal traffic intelligence analysis. Known threat is very easy to deal with, but unknown threat is hard to analyze. So using AI, introducing AI into the analysis of attack and abnormal traffic can make the analysis more efficient and accurate. So this threat model will might be divided three types. The outreach, spread, penetration, and these are the definition of these three threats. And this is how AI, what can AI do in to deal with this abnormal to unknown threat, these unknown threats. So thank you, and any comments, welcome.
Thank you. So are there any questions or comments? Yes.
Thank you for your presentation and the richness of use cases. My question would be, are these use cases something you already tried, and could you back up this with some performance improvements, KPI? Oh, you can't hear me? My question is, all of these use cases you've presented, is this something you've already tried, and could you back this up with some performance improvements, or are this for the moment just ideas where you think that it makes sense to apply machine learning?
The most of the use cases is implementing in our R&D developing, and a small amount of the use case and ideas. Okay.
But could you and do you have for any of these use cases, could you say we gained X% in some KPI? So my question is, you haven't shown any insight about how much do you really gain by using all of these machine learning based techniques? Have you experienced that it's really promising? Do you first experience confirm that it makes sense, or you don't want to comment on this?
Yes. Do you mean how many about the KPI?
How much do you gain?
But I'm not sure. I'm not sure now.
Okay.
I will refer to the materials in our the company.
Okay.
Thank you.
Other questions, comments? Yes.
Thank you for your good presentation. I want to ask the place where interact function could be deployed, because GT the production includes not only server or router but also device. So if we think about interact function, it could be deployed in the end device. So do you have any plan or roadmap to deploy interact function in the end device area?
In the end-to-end device, we are mainly focused on the network, and we would like to solicit some ideas for the end devices. Thank you.
Okay, so let's thank the speaker again. So our last talk in this session will be given by Heiko Link.
First of all, I have to apologize to the previous speaker. We were a bit too eager to swap the slides here, so you couldn't refer to what you were showing. I'm sorry. Run this from my laptop here. Now, thank you very much for having me. It's a very good occasion. I think it's a very good idea to have this focus group. There have been some suggestions what to include into the work program, and before starting my few slides, I would like to add to that, because I think what's missing a bit is the point of view of a carrier. So for the carrier, the network is not a purpose in itself. So it might be very nice to optimize the network, how it runs, but for us, it is a means of production, and it is a means to make money, especially in the context of a hefty 5G rollout, a business case, which needs to be justified, and it needs to be justified by the industrial use cases we can realize with that. So I think this should be a guiding principle for looking at the AI functionality ingrained into 5G networks. So that's what I wanted to start with. This is a very slim agenda, and I would like to start with an empirical view on AI. So what I'm going to say here is not mathematical, it's empirical. And if we have a generic AI project, as I try to pitch it here, then we see immediately the problem. So once we reach the third step, then everything is easy. Then we can take our established mathematics and bang away at a little problem until it collapses, and then we're in the clear. That's fine. But the problems we have is in the other steps, in the context analysis, in the configuration and tailorization, tailor-made configuration of the problem. I come from Telecom Innovation Laboratories, so that's the central R&D department, and we have in fact started an initiative which is more about methods. It's not about the N+1 mathematical technique of deep learning. We are trying to build an anamnesis chart, as we call it. So this is really stripping down the problem and finding which is the right way to attack it. That's what we're doing about the first two exclamation marks. And about the last one, I'm very thrilled to have learned about the interpretability from Wojciech a couple of minutes ago, because I think this can help us to extend what we are doing in the actual mathematics towards the business value we need to find. So the challenges we have is either on the one hand that the process does not scale. So in our innovation laboratories, we shouldn't be caught by just creating an endless chain of AI-related projects where we solve problem after problem and we have no scale gain in there. And the other one is that we need to find what I call the innovation delta. So most of the techniques we can get off the shelf, or we can go to our academic partners and get it. But we need to have a proprietary contribution to it coming from Deutsche Telekom. And the first idea, of course, is the infrastructure. And there, of course, the big bet is this one, is the 5G promises. Now, you have seen the slide before today. You've seen it in a technical context. And as I said, I would try to take another perspective, which is the business one. And this is now a clustering of use cases onto this same technological slide we've been seeing before. And there you can see it. It's grouped into extreme broadband, massive machine communication, critical machine communication. And if we now ask ourselves what kind of AI services is this inviting, then there are some immediate things which catch your eye. So predictive maintenance obviously is a well-established application context of artificial intelligence. Another one is the self-organization or organization of the IoT world. So this will create new problems which are not there yet once everything is connected. And then we have the industry 4.0 and the critical machine communication, including robotics or indeed power grids. So in the upper hand, you recognize the little icons for augmented reality, virtual reality, and the interesting thing there is what I see as device-borne decentralization, and this will be much of what I'll be talking about in the remaining minutes. Now, let's start with a little cloud in the middle. So this cloud translates in the 5G topology into an extended chain. And along this chain, you have several instances where you can do your computation. We've been seeing that before. The gentleman from Edgery has been talking about the intelligent edge. And well, we've seen it in other talks as well. And there are several instances in the 5G topology where you can do calculations. And my feeling is, and this really is the punchline of what I'm going to say, is this, that the AI solution should behave accordingly. So we should ask ourselves whether there is an optimal way to ingrain AI functionality into the 5G network. And then we should follow this fact that the magenta cloud can have any other color, sorry to the other carriers, it translates really into a chain where we do the computation. And now we can do that in two different ways. One is actually leaving our own realm. So outside the network domain of any carrier, here it is Deutsche Telekom, are the devices, and they get more and more powerful. You know, on the iPhone 10 runs the face recognition, which is nothing else than a trained neural network. So there is a powerful computer there we can use, or we can use the intelligent edge cloud, or Intel calls it cloudlets, I believe. So there's this option either to do it within the network or just outside. Now, what should be the decomposition criteria? This really is critical because it's nothing given. It's not a given fact that you have this type of computing power, and then you can tailor your application accordingly. It has to be played out, and it immediately has influences on the business case, because where exactly you place your cloud computation functionality. And how powerful you do it make, that depends on what kind of application or AI servlet may run there. I've given here some criteria as I see them. So obviously we have a local reach, but having said that, we know from physics that a number of local optima does not correspond to a global optimum. So we always have to ask ourselves the question, what compromises do we make here in going for local optima? The other one is the millisecond scale. So this, of course, plays on the 5G latency proposition. And then we should have minimal computing times necessary in this decentralized scale. We can pre-configure solution, obviously, and if possible, then automation. And also it should run on coarse-grained parameters which are available there. And this is something which is a qualitatively new proposition of 5G. There is a resilience option. If you may have backend connectivity broken, you still can run, if circumstances allow, your local compute, your distributed compute, and you can still remain, like in a coma patient, with basic functionality. Opposing that is the deep inspection in the backend, so that's the global embedding, and there you have longer response times. You may involve the human to advance the interaction. We heard a plea for that from South Korean Telecom. Now, this is not a reference to the Polish flag in honor of Sławomir and Wojciech. This is meant to visualize that the end device, we have the convergence of two different realms, really. One is the local context, and I've written down for you here the sensors we have in a run-of-the-mill standard mobile phone, today smartphone. So there's a huge number of sensors you have there, and you can. I even read that in Japan they have a Geiger counter in smartphones. So already, yeah. So it's very powerful for detecting your local context. But on the other hand, it's what we used to call in the carrier business the termination point of the network. So it has access to the global context and global knowledge, which comes from being connected to the network. This may sound a little abstract, but if you read here the the different use cases I put down. The first one, eCall. Gentleman from Volkswagen should recognize that this has a regulation history of upwards of 20 years, I believe. So the idea is that cars should be equipped with connectivity and with a sensor to detect a crash and then automatically dispatch the rescue services. Now, it's very easy to mimic this kind of service in a smartphone. First, you need to detect that you're in a car and you're moving along the road, and then if your accelerometer tells you that you have suddenly stopped and maybe you detected a flash of light or something, then such a call could be triggered. So, and this is just to give you an illustration of how powerful this convergence of the two contexts is we have in the 5G end device. Now, coming back from the end device, this is an example of a project we have been doing at Deutsche Telekom. It's from Smart Energy. And the important bit here is the microgrid controller. So we have a complicated local solution running, and the management, the local control of the solution is done in the microgrid controller. And of course, the 5G Edge, you already anticipate the punchline, gives us the opportunity to virtualize this controller function and put it into the Edge cloud. And then I put down two references for AI functionality, which are now not the focal point of the application. I do something artificial and intelligent, and then I connect everything around it. But here it blends smoothly into the energy management of what we have here in our neighborhood solution. The two examples are watching the anomalies in the power signal of the CHP unit, and the right hand one is especially fascinating because it is looking at the higher harmonics and even at the subharmonics of the 50 hertz, and you can detect any kind of appliance being switched on just from looking at the frequencies. So the point is that we have with the distributed compute here the option to have this smooth blend of artificial intelligence functionality in end-to-end use cases. This year's citing very briefly something we've been doing a year ago, the utility in Berlin, where I come from. The case was us, Deutsche Telekom, convincing the utility, which is quite a special domain, at least in Germany it is, that 5G is any good. And we, of course, were playing on the deep indoor and the radio characteristics and the massive connectivity you can have per cell. But again, here, as you can see, we compared that with the public 4G network, and we're showing that we're better. Well, you know how these demonstrators run. But in the blue box, there's mentioning of the utility network slice. And this now is a virtual concept as opposed to the real microcontroller from the other slide. But again, this slice could be the place where AI, you see their rules, where AI functionality may reside, as basic as it may be. In fact, we've been discussing with the gentleman from Stromnetz Berlin a very simple mechanism to detect blackouts. Today, it's the case in Germany, at least, that the sensor for a blackout is the customer, and if it phones into the network operations center and tells everything is dark, then they know there's a blackout. And we came up with some clever way how to detect this via the smart meters. And now, this here goes back to a central board member of Deutsche Telekom putting the human being as the role model for 5G communication. So it's a bit shady here, but you can see that there are the sensors in the upper left, and in the lower left you have the response, you have the actuator, and normally things are processed and computed by the brain, but there is a shortcut. You see these green line. This is the so-called reflex arc. That's a shortcut. And our feeling was that we can mimic this with the 5G infrastructure. I'll give you an example, again coming from grid management. So if we have an edge computing facility very near to the local substation, then we can watch at the substation just a very limited set of parameters. It could be the voltage drop, that could be the phase shift, it could be the frequency, that could maybe power signals. And we give us rules which we need to derive first. So this is an offline way of doing your AI. But once you have these rules, then you can detect whether your local grid cell is shifting out of the stable regime. And if you've done your analysis right, you detect that in time to do a reflex-like action. Now it's mimicking what we put down there from the human brain, and we can just address the registry there in the base station, sending load shedding signals to some appliances in the cell and stabilizing it. In fact, it would even work within a half wave of 50 hertz, which is 20 milliseconds. So this is it's a nice story. Of course, the story doesn't end here, because in the second step you need to involve the network operations center, and I would fully agree with the gentleman from Korea who said he doesn't feel comfortable with an empty one. There should be a person, and as you can see here is a person. So this is what I briefly wanted to tell you. I have no summary slides, but the two things for me I would like to give you as a takeaway. The first one is the application use case should be the guiding principle for anything we do in the design of the network. It's an economic truth for carriers. So, and the other one is that this 5G network with the distributed compute resource provides us with a unique opportunity to build decentralized AI functions. And they should, in doing that, we should get the load balancing just right. So that was it. Thank you.
Thank you. Questions, comments?
So maybe,
yeah.
So I just okay. I agree that this goes in the direction of distributed learning mentioned before, and I also saw your just iPhone with all these sensor nodes and things like this. So now the question is, I mean, as far as I know, I mean the current mobile networks have not been deployed to do big data analytics. So and then so do you think that and then on the other hand we have data available at different points, geographical points in the network, and then probably for example, if we would like to collect the data at one single point, we would have to transfer a lot of sensor data over the wireless channel and so on. So do you think that network operators will accept such solutions, because the core purpose of mobile networks is to communicate, not to do big data analytics. Okay, I mean just it's on top, but this is not just or maybe we have to think about, and this is just as input for our focus group, right? I mean, we have to think about new network architectures, that are better suitable for big data analytics.
But the point I was trying to make is that it's necessary not to transport all data, but only the relevant data. Of course, that's very difficult to decide what is relevant, but that would be the job of the AI engineers. It's not a job they have today. Today they need to recognize some pattern, and they train their neural network, and then they recognize the pattern. But this is it's a different job, but related to that, and it's making the problem fit for the 5G topology, and the topology fit for the problems there are. So I don't know the answer, but it can't be just sending the data everywhere. So it needs to be decentralized in a clever way. That's my feeling.
Other question? Yeah.
It's me? Okay, good. Thank you very much. Just introduce myself. First, thanks of all for this great presentation to Mr. Lehmann. I'm also named Mr. Lehmann. I'm Leo Lehmann, the chairman of the study group 13, who has established this focus group.
We cannot understand you.
Sorry. Okay. Please take your. You have your. Okay. Now I hope now everybody can understand me. So, just and I'm very interested as being the chairman of the hosting organization of this group. I have one question coming back to the presentation we heard from, I guess, Nokia this morning, and now your presentation. In Nokia, if I understood it correct, there was a case so far. One he could not identify or cannot identify use cases and application areas that couldn't be done, let's say, without AI.
Mm-hmm.
Looking now in your presentation, you give options for AI in 5G networks. Question one I have is this: is this an alternative? Is an option, does it mean it's an alternative to conventional technology? That's number one. And number two, if it's if we look at such option, has German Telecom already some idea how long it will take to train the system before they can really implement what's expected from them? Because I guess we talk about learning, so it's like an infant. In the beginning, the machine is stupid, and it has to be trained before it works. Is there already any idea what's feasible here? Thank you so much.
I'm not so sure about the second half of the question, because we do not have a complete rollout yet, and we do not have the actual physics how to split up the applications. But coming back to the first one, I think the point you were making was just ML for communications, and my point I was trying to say that the communication network itself is only means of production for delivering services. And my point is that we can ingrain AI functionality into the 5G network. So the ruling case from my perspective would be such a utility case. So to decentralize the stabilization network of the power grid. Now it's done centrally. And if we are able to bring that down to the decentralized level, that's a paradigm shift for electricity. Same is true for traffic management. So, of course, you have in the big cities, you always have people like us controlling the traffic lights, but you can think hard how in which bracket you may act locally and adapt what you do locally, and there's even a case for combining a 5G rollout case, this installation case by the people who are fitting their crossroad assistance onto the traffic lights. So that's a different perspective, I believe, from Dr. Hoydes.
Yes, I just take the opportunity to comment on this. I agree with essentially what you described. I share this viewpoint. Mm-hmm. But I guess the question then would be, if you try to push more, I would say, applications now into what we consider as 5G, is this a part of this focus group or not? I think that's a more high-level discussion. Is if you move away from using AI to optimize our networks or optimization or something like this, then I think we become open to a plethora of use cases that's outside true. Communication. Then I don't know if this should be part of this focus group or not. But,
yes.
But otherwise, I agree with what you said.
It's a valid point, but on the other hand, there could be a doubt whether there is a generic optimization goal for the network in itself. So I don't know whether a self-organizing network would organize itself in a different way for autonomous driving application or for any other mobile health application. And until we are not absolutely sure that there is a generic quality of the optimization, we should at least ask ourselves what's the volatility in the way this metric may shift. So maybe that's a good compromise, not opening the. I suggest that we. Okay, the last question.
Yeah. So in all of these use cases, how the network can respond quickly to the anticipated or predicted user demands. So if a given user or a given application demands certain bandwidths at some point in time in the future, and that demand is predicted by machine learning, how the network can quickly at the right time provide that bandwidth to the user.
It depends on the use case. So we heard about narrowband IoT. There is not bandwidth is not an issue, and in the use case I've been citing here for the stabilization of the power grid, you just need to push SMS to the appliances in the grid cell to shed their load. That's also not bandwidth relevant, and it can be done very quickly, and it can even be done without back-end connectivity. But as has been said before, you need to delve into the individual use cases and see what you need and how you can provide that. There's no general answer, I'm afraid.
Okay, so let's thank the speaker again. We are almost on time, but I suggest that we meet 6:20 as planned. Okay. It's 4:20.
So let's getting started. This session is for methods and enablers. We have 5 speakers, one from the remote side. So on this seat, our speakers are, the first speaker will be Professor Slavomir from Fraunhofer, and the second speaker is Professor Denis Kondos from London, and third speaker, Professor William Sarian from NIIR, Russian Federation, and that gentleman is Mr. Altaf Saik, Altaf Saik from Berlin. Yeah, yeah, just started. I'd like Professor Slavomir, the chairman of our focus group, to open up with his presentation.
Okay, thank you. I am here, the title of my talk, in fact, towards reliable and efficient reconstruction of radio maps. This was mentioned several times today. The results I'm going to present are not so new. I think that the first results we had 2013, but still we are working on this topic. And the reason why I have chosen this topic, because I think that this could be something for the focus group, and I think that it's an important topic, and that should be, maybe followed. I think we should follow, work on this within the focus group. It's a joint work with Renato Cavalcante, and I am both with TU Berlin and Fraunhofer. So radio map, first of all, is an unknown function that relates a geographic location to some radio system parameters, and then this could be path loss, capacity, or quality of service. In particular, I learned from Volkswagen, but also BMW. They are, for example, interested in latency, which is, I think, quite challenging to predict latency, for some positions. So in other words, you can imagine here in this room, I mean, we have some measurements from users. These measurements are collected anyway in networks, and we would like to have some reconstruction or prediction with respect to some quality of service parameters for points where we have no measurements. Yeah, I mean, because, for example, I know that in 2 seconds I will be there, and I would like to know what the capacity or what the QS can be provided when I am there. So, and we have been working on this topic. We call this reconstruction of radio maps, and we are mostly interested in an online algorithm. So I don't know, because we have not talked about this in this depth. But you have this batch algorithm where you collect the data and then analyze the data, and then you have online algorithm where you just, when measurement arrives, new measurement arrives, you take it into account to provide better prediction. So, okay, maybe, in general, what are the challenges, opportunities in wireless networks? And that's why I just, was happy about this focus group, because I think that we need something like this. First of all, we have high mobility, okay, so which means we have network topology changes in wireless networks, and wireless links exhibit a thermal and dynamic nature. And here, I don't know, usually we talk about maybe path loss on time scale of hours or minutes, but if you, for example, want to enable some functions, you also have to talk about time scales of milliseconds and seconds, okay? So, and then we also maybe forget that, channel and many functions are non-stationary. So, even, if you learn statistics, then maybe, you cannot stick to this. You have to relearn, because just, everything changes, and then you have a lot of, you have to do with issues like non-stationarity and, of course, non-ergodicity. Also, noise capacity limited transmission and exposed to interference. So wireless channel is error prone and highly unreliable. So that's why I just, asked today, Heiko, I mean, we cannot collect all this data at one point. We have to do, in fact, distributed learning, and maybe we need to know something like new network architectures for big data analytics. When I mean network architecture, I mean also functional architecture, not only just, where to place base stations and things like that. A problem is stringent requirements of many 5G applications. This was just, when Jakob was talking about, today, he said that models are good. My experience is, I mean, we have a lot of projects in the area of Industry 4.0. Then if you go to reliability of 99.99999%, then, the model is not good enough. And then, if on top of this you have, latency constraints of 1 millisecond, you cannot repeat. I mean, there is no way to, repeat transmission and so on. So that's why data is distributed in different locations. This is another, reason for doing distributed learning. But maybe on the positive side, we have a lot of expert knowledge. I mean, we have been working on this for many years, and then we understand wireless systems quite good. But the problem is, how to incorporate this knowledge in a systematic way into algorithms. And then another thing is, there is a lot of structure in the channel, signals and functions. I mean, so it means that we have, a lot of correlation, sparsity, and then this should be exploited. But the problem is, for example, how to exploit this in real time, because if we have this low latency, constraints. Okay, so here the focus is, I will, use this example to show you, that the problem is not so easy. And I would take the example of capacity maps. Here's an application of using a capacity map. You have a car, you know the trajectory of the car, and then you can predict that there is, overloaded cell and so on. So then you can avoid transmission in the cell, especially, for applications like video streaming and so on. So, and we were talking about the data today. The data is, of course, a big problem. So one thing is, of course, we could use very sophisticated simulation platforms or models. One was developed in this project Metis, and this is what we took as a basis for the evaluation. For other radio maps like path loss and so on, I mean, some data is available you can use to validate your algorithm and so on, but in general, this is a big problem. Maybe, a way to go is certification of data. So just extract some parameters from real data and then generate, artificial data with the same parameters. Maybe this is, one way to proceed. So, okay, here, if you want to learn these capacity maps, and this is an important point what I would like to make here, is that it's not enough to learn, channel, I mean, path loss maps and so on. The reason is that you need, to learn several ingredients. And the reason is that wireless channel is a shared channel. So if I communicate with you, I talk and everybody can hear because we have this broadcast property, and it doesn't change if you go, with frequencies, up to 2 gigahertz and 6 gigahertz, okay? So that's why there is, this coupling, and this coupling is really, is highly nonlinear, and causes some problems. So you need to learn several things in parallel to get, reliable information about capacity. So it means capacity conditions where you have no measurements. Okay. So what you need is, first of all, path loss map. And here, because today we have been talking, about machine learning, and I think that many people think, okay, machine learning is about neural networks. Neural networks this is, one-to-one mapping, but there is also something outside of neural networks, and so you have, say something between signal processing, machine learning. Okay, I mean kernel-based methods, and this is what we used for path loss map reconstruction. And here's also a reference. And in fact, here's the scenario is quite easy. Each base station has access to path loss measurements, so we could use these RSRP values and make this prediction of path loss in its area of coverage. Whenever a new measurement arrives, the base station updates its current approximation of the annual path loss function. So it is, online algorithm. We have to cope with errors and so on. And of course, we would like to have high estimation accuracy and adaptivity and good tracking capabilities. I mean, it's not like, we learn and then we are happy. We have to relearn. In fact, we have to track permanently. And low complexity or just distributed learning and robustness to error measurements or things like this. So this is, example for this matrix scenario. Okay, I forgot to mention here that you have this, matrix scenario with buildings. This is gray areas, and you have base stations, pedestrian area, and these are roads and things like this. And then, path loss means here this would be path loss for some specific scenario. This is what you have for this artificial scenario. So, red means that you have good channel conditions. In fact, I mean, the path loss is not so big. And then, if you go to blue, then there is strong path loss, and then maybe you have fading effect. You cannot just receive anything. So, okay, so we can do then, you have this traffic map. I mean, for traffic map, I mean, this was also today in several talks, and the topic is really old, and we also had the possibility to work with real data from the network. I mean, from real network. And then it depends. I mean, if you have accumulated traffic, like voice traffic, so our experience is it's relatively too easy to learn, and using Gaussian processes and things like this. But if you have something like this, I mean, data download or not accumulated, then it can be extremely difficult to learn something like this. I mean, our experience is that you're not able to learn or predict this, from observing one time series. You would like to observe, have more global observations in the network. So, but sometimes, and this is, my point, sometimes you don't need to learn. I mean, sometimes you are only interested in some upper bound. So you want to learn upper bounds. For example, you want to learn upper bound that the traffic stays below, this upper bound with high probability. Yeah, this is another task, and it's easier task. Of course, not optimal, but this is sufficient for many applications. And in the end, I will show one application for this. So here, I mean, for this Madrid scenario, I mean, learning data traffic, would be something like this. As before, we would divide this area in more small areas. And each area represents, some traffic demand. This is what we have to, I mean, this service would have to provide, to make everybody happy in the network. Okay, so, and the last thing here is about load. And load estimation, load is defined as the fraction of used resources at the base station to all resources available at the base station, right? And the load depends on many things. It depends on the channel, depends on interference, it depends on traffic, depends on powers of other users and things like this. And the important thing is that this coupling is highly nonlinear. In fact, I mean, the load is a fixed point of some function. And that's why our experience is that if you apply here some standard machine learning methods, I don't want to say that you will fail, but you won't be able to learn this load, this coupling fast enough for many applications. So here, just what I wanted to mention is the following, that, for example, here, this is a good example where you can match expert knowledge with machine learning. So, in fact, and this is what you should do. I mean, this simulation shows here you have something like training samples and the arrow on the y-axis, and then here blue and red are some standard machine learning algorithms. And you see that this Gaussian kernels, I mean standard methods. This approach is even better than our approach if you have enough training samples. But the problem is that for many applications you are not interested. You cannot wait so long. You have to make decision. Maybe after 100 samples, and then because after that everything changes. And then the information is useless or is not available anymore. So that's why, and then to accelerate this process, you should even exploit the structure. I mean the model which is available, and then for example do something like model predictive control or things like this. So in order to learn the parameters of the model, okay, and then you will be able to accelerate this initial speed of the algorithm. Okay, I mean here's an example of such a load map, and you see that there are some areas here for this snapshot with highly loaded base stations. And then usually, also network operators are interested, to keep a load of base station under certain level, which is again a different problem, because you have to predict, level, and you say that that the base station and the load at base station will remain with high probability under this level, which is different from learning the load, the actual load. Good. So here is in the end, if you combine all these ingredients, then you can predict capacity maps. Here's again snapshot. I had a video, but it's complicated here to start a video, so that's just only one picture. On the left side, you have the original capacity map. You see that blue is very bad capacity conditions, and red means at really good, up to 5 megabyte per second. And then this, if your video is changes, it's just like a changing picture, and then you have to track it. And this is what you can do with these methods. Of course, now the challenge is to go down. I mean, for example, the question is, can you do it on fast fading level? So within 10 milliseconds or something like this. Because I think that for many applications to have high reliability, it is necessary to do this learning, not on, say, minutes, on the timescale of minutes or even seconds. You have to go down to milliseconds. And this is highly challenging. Good. I mean, one example is, and it's energy saving optimization. That I think that even in current networks, I mean, the most energy is used for, it's a static energy, to run hardware. Even if you don't transmit anything, the hardware consumes energy. And then there are some studies, I think, from Nokia, that 60-70% of energy is static energy, so air conditioning and things like this, and then 30% or 40% is just transmit power. This may change in 5G, I don't know, but this is the current state. And in fact, if you want to say minimize or reduce significantly the energy consumption in wireless networks, you have to switch off network elements, right? If they are not necessary. And like several years ago, I mean, network vendors were interested, to do it on the timescale of minutes and seconds, not just between day and night, just in very short time scale. Okay, so you can do it. I mean, there are algorithms how to switch the network elements, but the basis for this is just a capacity maps or prediction of capacity maps. Because once you say, I mean, that I can switch off network elements, you have to ensure that the load in the network will remain low for significant long time period. Okay, so because otherwise, if you have these fluctuations in, and then you will try switch off and switch on network elements, you will get oscillations in network due to interference and so on. You cannot just switch off probably amplifiers and then switch on. That this can cause oscillations in the network. So that's why you need reliable prediction, and that's why just this was one example of this application. I even know that from the decision column this was just a project, and they brought this to 3GPP standard. And for example, we could show that you can if you do it, you can reduce the number of base stations. Here, this was from real network from 900, down to 440 base stations. So you could switch off without violating the quality of service requirements. I think that I should finish. Yes. Okay. Okay. So this is the last thing. Maybe one point. I mean, what we are working on right now is just this any-to-any radio maps. I think that David also mentioned this in his talk, you know, reconstruction city, nah? You can just reconstruct buildings and so on. So here, you know, you would like to reconstruct path loss conditions or channel conditions for any 2 points. Nah? And then so that's why you could reconstruct walls and things like this, objects. You could use this for tracking, localization, many things. I think that there are many applications for this. Okay, thank you for your attention.
So we got some. I think we will not be able to finish by 6 o'clock because we have five presenters and he spent more time than he promised. He promised in the beginning he's gonna skip his presentation, but it's okay. So because the presentation content is just great. So let's take just two questions. How about that? Yeah. These two yeah. How about this gentleman and that gentleman? Because you did a lot. So yeah.
Yeah, I have a question regarding the image reconstruction approach. Do you have an image processing approach to this problem? In a sense, yeah, when you apply the kernel methods, or are you using physical models that would explain how the path loss is created, you know, from physics?
In the first case, we use multi-kernel. So we provide machine with more than 1,000 kernels and then impose sparsity to choose the most relevant ones. So it's not, you know, image processing. I don't know whether they use some methods like this, but for this any-to-any we use, you know, for tomography from medical, because they have the same problem in, you know, if they take measurements, you know, of the body, and then they have to reconstruct, you know. So mathematically, you know, the approaches are very similar. Yeah. Yeah, I forgot to mention that, you know, this is not classical pathos. You have also random component shadowing. So this is, of course, I mean, we use it, and this is just, you know, this knowledge is used by the choice of kernel functions. Yeah, so here is the bridge between machine learning and expert knowledge, how to choose the kernel functions.
Okay, thank you. Next question, please.
I have a question regarding the construction of the methods of the radio maps. The construction based on are the feature collected for area or per link? That's I mean, what I think now, if you have a car, we should be able to predict the quality of service for certain KPI like latency or data rate capacity per link per users, but to the mobile station. And that I'm asking if that data which has been collected is over the whole area, considering all base station for static points, or did you also consider the mobility aspect of the users?
Okay, so here we don't consider mobility aspects. It's reconstructed for the whole area, but of course we don't have measurements for the whole area. We only have measurements for some points, and of course the more points we have, the better the reconstruction is. But the challenge is, you know, to reconstruct the whole area based on some few measurements and using context information and things like this.
One last question. Please compress it.
Thank you. I have a question from Ashwini Setnoor again. In certain situations, could there be a possibility of existence, variations in the expected predicted values? and the actual sorry. In certain situations, could there be a possibility of existence of variations in the expected predicted values and the actual values? And how would this variation be accounted for?
So this is about timescales. It depends on what timescale you perform this prediction. So here, of course, I mean, if you do it for self-organizing networks and so on, so many things are averaged out, many effects. I mean, I'm not talking here about fast fading, and I am here talking about just some kind of long-term channel variations. Of course, I mean, this is machine learning. I think that for some algorithms we could provide some confidence intervals, but I cannot answer these questions in general. What is the error and things like this.
Thank you.
Let's give him applause again. Our next speaker is Professor Dennis Gunduz from Imperial College London. He's going to talking about reinforcement learning for wireless network optimization. Please, Professor.
Okay, thank you very much. First of all, for the invitation. It's a great pleasure to be here. So I kind of coming up with the talk topic and what to put inside in the slides was a bit challenge, of course. First time presenting at ITU. So I thought, as Slawomir also mentioned, a lot of people think like deep neural networks as the machine learning application. So I thought maybe not as many people might be familiar with how the reinforcement learning can be applied for wireless network optimization. So I'll go over that for those of you who may not be very familiar with what it is, what it does. If you already know, so it's not something new. And I'll just give two examples of how we use it in my group. Okay, so I want to start with this a nice quote for what I think the machine learning would bring for lots of areas. So this is from actually just this weekend, just introduced quote from in Davos. So the pace of change has never been this fast, yet it will never be this slow again. So I think we are kind of in that period that in kind of every technology area, so the things will change very fast, and I think machine learning over the next coming years will enable this acceleration of change in many areas, including wireless communication. So this is kind of my view. Okay, so where does reinforcement learning fit in? So in a nutshell, reinforcement learning is an agent-based learning framework. It's nothing but actually an optimization. So for many people have been doing control optimization theories, it may not be something completely new. So here basically there's an agent in an environment, but the main issue is that this agent is interacting with the environment. So there's some set of actions the agent takes, and these actions have an impact on the environment. So the next time the agent has to take an environment, so this will be based on previous actions, so on and so forth. And there is this can be considered as a learning by trial and error. So you do things, you observe, and then based on the outcomes, you try to improve your policy or your strategy. So why is it different than supervised learning? So actually, I would argue that it's much more general than supervised learning. Supervised learning can actually be formulated as a special case of a reinforcement learning problem, and actually is used widely as within reinforcement learning. So here there is no training data, so you don't have explicit feedback based on your decisions. For example, nobody tells you when you see the image, nobody might tell you whether there's a cat or not, that decision is correct for that particular image. So here in the reinforcement learning framework, actually I would like to use Merouan's example. So he gave this example of when you want to score a goal, either you kind of use all this kind of model-based approach, you use all the physical model to optimize how you should kick the ball to score a goal, or you can just do this many times. and then just choose the one, every time you see, is it a goal or not? And then next time you can just repeat that. So this would more fit into the supervised learning. So you do it, you observe the outcome, and then you know which is the best. Whereas I would claim that reinforcement learning would model the whole game. Okay, so you start the game, you do all your tricks, and the goal is to win the game. You can, for example, choose to run non-stop the first 10 minutes, maybe score a few goals, but then you'll be tired and you won't be able to play the rest of the game. So it's kind of a long-term optimization. And here the feedback, nobody's going to tell you at 10 minutes whether you are going to win or not. So you have to wait until future, and your objective function will be an accumulation of all your actions, the results of your actions throughout the game. So in a way, the learning happens online as you go on interacting with the environment, and you have the feedback is in the kind of implicit in the form of this reward cost based on your actions. Again, it could be you might not get any feedback until a certain time frame, so you might just get the feedback at 90th minute when you just won the game or you lost the game. So the main challenge here is the exploration-exploitation trade-off. So what does it mean is that, so you can play this game many times. So the trade-off is that, of course, you want to play different techniques, different ways of playing. You want to see which is the best. But in the same time, of course, as you do these, you don't want to lose all the games until the point that you learn. So now this might lead to actually two types of challenges, which I will maybe talk about a bit more once I mention about this deep reinforcement learning. So these are actually, I think, even though a lot of people think as machine learning as just deep neural nets, a lot of the kind of most significant, successes of machine learning that are kind of in the news recent years are from reinforcement learning. So starting from, again, it goes back quite early. I could actually also include here, as Merwan mentioned, Shannon's work, but in more kind of machine learning literature, Minsky's work is it's considered as because it's more in the form of today's reinforcement learning modeling. So then, in the 90s, people first, solved the backgammon. It's quite a simple game you would think about, and more kind of maybe interesting, different from a simple game. It was the helicopter autopilot using reinforcement learning, basically just learning to fly. It's in early 2000s, and came this DeepMind's kind of famous series of famous deep reinforcement learning results, starting from their high human level performance in Atari games, where actually. So the main kind of significant thing was that they did not use any kind of the rules of the Atari game. So they were just simply getting the pixel values in the screen, and just based on the result, whether you won the game or lost the game, they were coming up. The deep learning algorithm comes up with the optimal strategy, and then they expanded this to the AlphaGo, beating the top human Go players. And finally, AlphaGo 0 from last year, basically. So the AlphaGo still had to do like hours of training based on all previous games. So it had to kind of train based on this huge history of knowledge. Whereas the AlphaGo 0, just you give the rules of the game, it just learns. So it doesn't. You don't need to give any kind of example. So it simply learns everything from scratch and actually beat the AlphaGo 100 to 0. Sorry.
I think they played 100 games, but the result was, I think, about 30 to 0. Or, there were like 70 games that ended in a draw, and then maybe 30 or so won. So
which one? Sorry, are you saying for the AlphaGo or the AlphaGo 0 with the AlphaGo?
The very last one. Sorry, the very last one.
I mean, this is as far as I know, it's from the DeepMind, and this.
It wasn't 100 to 0. It wasn't 101 and 0 lost. There were quite a few draws, but that's a minor.
Yeah, I don't think. I mean, basically, if you train enough, I guess it would end up in. Depends on where you stop the training. Okay, so now what's going on? So in the sense, so I talked about this kind of reinforcement learning framework where you learn. So where does this deep neural net comes into picture? So the goal in kind of any reinforcement learning is to understand the values of your actions. So typically, either you learn different, when you observe a certain state in this evolution of, interacting with the environment, when you come to a state, you know what is the potential value. So from there, following some optimal actions, what will be your expected outcome at the end. So the goal is to learn this. So if the game is simple, for example, you can think that here in a game like Go, or you can consider a simpler game, all the rules are deterministically known. So there is, apart from the opponent's actions, there is nothing random. And actually, if the opponent is following an optimal strategy, everything should be deterministic. So here the challenge comes from when you map your states or state action pairs to values, the state space is so huge that you cannot actually really learn this function. So you have to do some approximation, which means that you reduce the dimension, you come up with a much simpler approximation, and this will also kind of limit your possible exploration. So you cannot possibly explore all Go actions and all Go plays. So you have to only explore those that are relevant. And you have to, your learning algorithm has to somehow extrapolate. So you cannot have a value for every possible state and action pair in the game. So actually this of course has problems. That's why, for example, the AlphaGo actually lost one of the games, because the human player did something that was considered unlikely. So the game never explored that option. Now, on the other hand, here, one thing that I want to note is that in this example, for this kind of problem, so the learning can happen in a complete simulation environment. So you have all the rules, so you can repeat this, and this is what the AlphaGo Zero does, playing with itself. So basically, you can just repeat it as many times you observe all these things, and then you simply improve your strategy. Now, whereas, let's say, for more kind of real-life type of applications, maybe for wireless networks, there is another challenge, which might or might not, be the case for the particular application that we want to we focus on, is the fact that sometimes you might not have you might not be able to run this thing. So this is, I think, one of the things that came up before, whether you can actually do these things in a simulation environment. Would it work, or do you actually need the real data? I think the answer to that is twofold. So you can just run the simulation. So today we have the simulation, and as mentioned before, so basically we have very good tools that we optimize given the model. So this is more the, kind of this physical approach. So we know the gravity, we actually optimize where we should kick the ball. Now, but in real life, the model can be different. The gravity can be slightly different. There might be wind, etc. But our experience tells that more or less these are good enough. So the wireless networks seem to work reasonably well. Now, if that model is good enough for us to do optimization, that should be good enough to do reinforcement learning as well. So we can actually run that model, whatever, as long as the simulator is good, we can run that many times and optimize our policies. And it should be fine to some extent. But of course, if the reality is very different, then it's not going to be the case. And the challenge there is that, of course, so one thing that I mentioned, so you might not be able to run all possible realities. So I think that this kind of challenge is happening more for this kind of 5G as the diversity of use cases expand. So, and just mentioned in the previous session is that, one application might require completely different type of actions, and it might be very difficult to run all possible scenarios for all possible objective functions, objective applications, and then kind of record those for every possible network node and then use those optimal things. So this means that actually your agents, whatever communication nodes, might learn some of the things as wherever they are deployed, whichever application, objective requirement they have, etc. So that kind of makes the challenge that now you really have to learn in a kind of this interacting with the environment. And now the training part, which is the training of the kind of supervised learning, which is the exploration in the reinforcement learning framework, consumes resources. So it's not something that you run at home and then you optimize your learning and then now you go play with the Go player. So here there's a cost in terms of spectrum, there's a cost of power, there's a cost of latency to collect all that data, train your network. So now it's much more essential to really understand this exploration-exploitation trade. Okay, so one thing that also, particularly for the, I think the wireless network, in general network design with this kind of reinforcement learning approach is this kind of distinction is this proactive versus reactive. So now the main issue is that, as I said in the reinforcement learning framework, you take into account the future impact of your current actions. So meaning that you know the possibilities, the future possibilities, so you do things proactively rather than the current networks where most of the things are done in a reactive manner. So this is probably going to be the distinction between current networks and the future networks, which might exploit much more the machine learning techniques. Okay, so what are this kind of proactive network design? So these type of networks should explore as much as possible, learn the network dynamics. They might use the model, as Slawomir mentioned, the expert knowledge, but they need to combine that with the data. And based on this limited knowledge, as much as possible, they need to exploit the limited resources in the best way possible. So this will allow user and context-dependent resource provisioning. So which means that now you can actually know your users much better. So it's not just the network is not anymore just a commodity kind of data provider where anybody comes, connects, gets certain rate, and then whether they're happy or not, who knows. So now you can track actually what your user requests based on the past, based on the similar users, and the network condition, etc., and you can deliver much better service. And of course, this is also the kind of, as I said, okay, many of these techniques have been around, so control theory, optimization have been studied. So what's new? Of course, the kind of the two things have been mentioned many times, I guess, and they are obviously true. So one of them is the huge amount of data available. Then the second one is the amount of processing power available. So they changed the kind of the framework. And then one thing I would like to emphasize that why this kind of machine learning approach today is different than the classical control theoretic approach is that because the attitude is different in the sense, so the control theory has always, and also I think this is true for most of the wireless communication work we have done, is that so we model the network and we try to solve the optimal problem. So what is the optimal beamforming, like the rate assignment, etc. Whereas in this kind of reinforcement learning type of approach, you don't want to optimize necessarily everything for that current setting, but you want to learn in an incremental manner. So for example, actually the deep neural net, they do stochastic gradient. They learn from every single sample, so which is an unbiased estimator of the gradient. But if you do it enough on enough number of samples, it turns out that you actually approach to either the optimal global or the local optimal. So this is the type of different attitude which we can also exploit in the wireless network scenario. Yeah. Okay. So I think actually, so this slide I was going to mention what are the potential things that we can actually learn and exploit, but all of them have been actually mentioned in one or the another talk. I was going to mention also, Marianne mentioned the multi-arm banded machines that have been very widely used. It's kind of a special case of a reinforcement learning problem, which in my opinion could be a lot of applications possible in wireless domain. So one of them, content placement, that we have done some work. And again, so very kind of, especially due to the time frame of the problem, I think the content placement, caching, and media streaming is a very, very good use case for using this kind of reinforcement learning framework for wireless network. So I had an example. So here I want to mention this very kind of briefly because to make one point. So again, even though I mentioned how successful the deep reinforcement learning, it's not the only way to do reinforcement learning or learning in general, and actually it might not be always the best way to do it. So I am afraid that in the coming few years, at least from the academic kind of perspective, we'll see lots of papers coming with deep, like reinforcement learning for X, Y, Z, and it's fine to explore these things. But I mean, the fact that you can actually run a deep network and get some results doesn't mean that it's the best, thing to do. there might be much simpler thing, because that's even though we don't know why the deep neural nets work very well for lots of things, but there are some kind of heuristics that that the problem should have this kind of hierarchical structure, which might not be there at all in our wireless communication problem. So, for example, in this work, we had a huge state space of content, different random lifetimes of content, random demands from users, random channel conditions, etc. And our goal was to kind of deliver proactively with the minimal cost to the users. So we formulated this. It's a huge kind of reinforcement learning problem. We said, okay, let's do some approximations. It's common in reinforcement learning. And it turns out that if you just do a very simple linear function approximation, so here you can see that you get very close to actually the theoretical optimal, that lower bound that you could get. So if you do the deep reinforcement learning, maybe you can improve, maybe you don't. But the processing power that would require is an extra cost that probably is not needed at all. Okay, so I'll skip this. So some other things that I really want to mention are that we are doing. So I wanted to mention, so should I just wrap up, or is there like 2 minutes? Yeah. 2 minutes? Okay, so maybe some high level thoughts that, so I think actually we have a good kind of place to apply machine learning. So we have this wireless platform, we have a lot of data, we have like users who want to benefit. I think we can actually exploit the machine learning a lot. So I'm not so, let's say, pessimistic. On the other hand, I agree with Jacob that we don't have yet good kind of like targets, which I think should come from industry. I think that is the kind of the key of the success of all this kind of machine learning in industries like all these more software companies. So they have a certain goal, they have a certain performance measure, and they can even they provide the data. You can compete very kind of openly. So I think that kind of problem should come from industry. Should say, okay, this is what I need. I need this much reliability with this data, and can you do that? And actually, it would be great. We could have this open data, open and maybe even competitions, etc. So for well-defined performance targets. So for example, one of the things that's been mentioned is 99.99% reliability. Well, I think, yes, it's very interesting. On the other hand, given that most of the machine learning algorithms, we don't know why they work and when they work, it's not clear actually they are compatible with that kind of requirements. But I think it's worth exploring. And one thing I want to mention is, since there are a lot of industry here, is the lack of talent. So in my opinion, right now in the wireless industry, a lot of people want to use machine learning. I think a lot of companies don't have the people that can actually know what it is about and where to use it. Excluding those here, of course. I think, and it will come in the near future, but I think they need to invest a little bit in the kind of to the academia. Because if you see, a lot of people from very good machine learning groups are going to companies like Google, Amazon, Facebook, Uber, etc., and they do amazing work. I'm not against that at all. Like talent going from academia to industry, but I think we in the wireless community we need that more. So this kind of support from industry to the academia to train the right kind of talent for this particular area. Thank you very much.
I knew that. Yeah, okay. Please make it short, okay? So let's start with.
Yeah, Dennis, thank you for this great talk. 2 things concerning talent. I said this in my talk. What we have experienced is it's actually much easier to train domain experts to be able to use machine learning than do the inverse. So I think that's a common trend. So what everyone's doing. So I think this shortage of talent might be very temporary, but I think most companies are ramping up very quickly. But my second thought goes about the problem with reinforcement learning is, as you said, that it takes so long to train. And for example, AlphaGo has played thousands of years a human would have taken to play all of these games. And I think in wireless, if you use reinforcement learning, even if you have a real system on which you could try these things, you don't want to wait months until your algorithm has converged. In order to speed up the learning, I come back to this idea of having a digital sibling or clone of a network being able to simulate millions of plays of Go, simulate millions of hours of a real network. And what do you think about this?
I mean, I want to kind of make that point actually. So if you can replicate your model as accurately as possible, then you can definitely do that. There's nothing wrong. You can learn it in the lab and then go and deploy. But there will be applications where it won't be possible because you might need to deploy your system in a completely different environment, in a completely different kind of radio environment. So if it is possible, that's definitely the right way to go. But even on other type of cases, I think there is still, then obviously you won't be able to achieve the performance of the AlphaGo. I mean, with even time and the processing power. But that was the kind of the point that I wanted to make at the end, is that even very simple, linear function approximation might actually get you a lot. So I think we have this kind of precondition that, oh, this deep reinforcement learning is doing great, so I need to use that. I think the opposite, as in also, for example, so Gaussian process is a very strong, very powerful tool, and it gives you not the result, also the reliability of your result. You know with what probability you actually have learned. Maybe we need that. So I think that basically we need to look at the right kind of solution for the particular problem. Okay.
Thank you for the clarity of the presentation. Sorry for this basic question. You mentioned in the reinforcement learning that there may be different ways to reduce the space state. So the question is, in the context of standardization, this focus group or in perspective in general. So is there an expectation that we have guidelines in terms of tools, solution depending on the application use case for optimizing this and reducing the space state? Thank you.
Yeah, I think very good question. I haven't thought very careful. I mean, very much on that. Even actually, I mean, for example, for many of the tools like the neural nets, you don't even have any kind of result that's convergence or anything. Your learning might not even converge. So there are no theoretical guarantees. If you do linear function approximation, you know it will converge, but it will converge to whatever the best thing for that. So you don't know how far it will be from the best thing you could do. I mean, I think that problem is very difficult to solve, and I think it also kind of connected to this issue of the reliability that we would like. We want 99% or even 80%. Are we going to know it? Yeah, so it's not clear. So maybe for that, Gaussian processes are a better tool, in which case you actually have a reliability kind of result.
Okay, fourth row.
Thank you, Mr. Chairman. Please, I want to seek some clarification considering open data. In your opinion, and from the advanced nations, both in the academics and in the industry, how open are the industries to providing information and data in case you want to conduct some research? 2, is there any standard compelling these industries to be open with their data? Am I clear?
Yeah, so I mean, it's very hard to say how open in the industries. I mean, I think from the academic, when you look from the academic side, almost everybody complains about the lack of data in our community. I think we need this. So this is what I wanted to emphasize. And we need this kind of attitude change that happened in more kind of the traditional machine learning kind of communities. There's all these Googles and etc., where they kind of made this huge leap thanks to also this openness. If you go a lot of this, like examples like TensorFlow, etc., their algorithms are open, their data is open, so it's a much more kind of open environment. Now, of course, there are kind of business reasons for maybe not doing this in the wireless environment, but wireless, industry. But I think that also prevents, obviously, the development. So if we don't have the data really test, I mean, it's of course harder. I don't know, for example, the standards. I mean, maybe that could be a good way of encouraging, like to open this data and then let people actually test their algorithms on available data.
Next one for Reinhard.
I need to correct myself. You were right. I was wrong. So alpha go 0, as you said, beat alpha go 100 to 0. I mixed it up with another paper that was published by DeepMind in December. And that was a chess program called Alpha Zero. And they played and this program played a 100 game match against Stockbridge, which is apparently the best computer program so far. And here the result was 28 wins. I looked it up, and the rest 72 draws. But you were right here on your example.
Thank you, Professor Kundas. Our next speaker is Professor William Sarian. He will talk about using the information control networks as a test area for searching for effective methods of machine learning in the networks of the future generation. Please.
Machine learning technology, in my opinion, have won until the resolved question how to organize the procedural certification. It's a very important question. And I, in this short describe of recommendation of IoT, requirements of information control network and related application, then I review the main function of ACN operator, the possibility of using ACN as a test area for machine learning, and other described perspective. Already today, fixed and mobile convergent network generate a huge amount of data at the level of the network infrastructure and the user level. The rate of increase is such that there is an opinion that with when even 5G networks cannot cope. Therefore, the creation of focus group aimed at the solution of this problem is very relevant and timely. The purpose of our presentation, is to talk about the potential of existing information control network, ICN, which solve similar problems, for a more limited number of tasks, and suggest using them as a test area for machine learning. Information control network is a logical network providing service over, for example, infrastructure NGN or digital television infrastructure characteristic by high reliable data transfer, service management, and traffic control. ICN always the organization of a trust environment for the provision of mission critical service such as emergency management, e-government, e-commerce, e-health, by introduction an ACN operator as a single point of service management. We note that one ICN operator simultaneously provides only a limited amount of service for limited We note that one ICN operator simultaneously provides I repeat. We note that the one ICN operator simultaneously provides only a limited amount of service for a limited number of users. ICN operator users obtain service from ICN operator using the infrastructure over this ICN is deployed. all ICN users have enhanced support the ICN operator that is responsible for service provision and service management. In this network, many issues which are problem in construction machine learning are solved. Example such as how and who to respond if the result of provision of service is a disaster that may be happen. As you can see from this slide, all interaction between users, called ICN users, and service provider, called ICN provider, are made through the special ICN operator. The main function of ICN operator to create for specific ICN typical process that will be regularly reproduced in this ICN. Note that reproduction of typical process take more 75% total traffic of global network. The number of those typical process must be limited. Those processes must be interrelated, semantically harmonization. Under those typical processes, it is necessary to find ICN users who need those typical processes and select one or more ICN service provider or providers that can ensure this implementation. Note that all user decision ICN operator has certification operated certification. I continue the main function of ICN operator. It is necessary to provide training for ICN users of the correct implementation of typical process. Therefore, this procedure for change, the rules of the formation and operation of this type of this typical process in ICN, for example, with the aim of improving them. Forming and functioning in real time of typical process administration system for ICN service provider and ICS users. A procedure should be developed for shutting down uncapable ICN service provider and those ICN users that not train and not complain. The possibility of using ICN as a test area for machine learning. Thus, we note the similarity of task of ICN and machine learning system. The machine learning application points in the ICN are the ICN operator and ICN user. Studying the roles of ICN, machine learning system developer could determine the time frame and necessary and sufficient degree of learning machine learning. How to choose hyperparameters that essentially define the knowledge base. How to ensure the process of knowledge translate deep learning and other important characteristics of machine learning, including how to build and service administration system. In turn, the use of machine learning methods in the operation of ICN operators, the ICN service provider, and users of ICN can improve the efficiency of ICN. Of course, all those assumptions require detailed research, which we would like to within the framework of our focus group. In conclusion, I need say one caution. It should not be possible for machine learning and artificial intelligence system to interact directly with the IoT and other source of data for big data, since the result of such direct interaction may be the birth of the new knowledge inaccessible in incomprehensible to man. It's very, my opinion, it's very important cause. Thank you.
If anybody has a question, just no question. Because the remote presenter is, I guess he's waiting for connection. So please send him with the. Let's give him a big hand.
Speak about this my presentation during workshop.
Okay. He's gonna talk this subject during the meeting time. So we're gonna have another chance to hear from him. So let's give him applause. So if the remote presenter connected, then please put him on the. Okay. Next presenter is Mr. Elena. Ms. Elena from Amazon. Yeah. Let's get started.
Hello.
Yeah, yes, please go ahead.
Hello, I'm Elena Ehrlich. By background, I am a mathematician. I am a data scientist on the AI global team for Amazon's professional services. To introduce myself, I have not a research background in telecommunications, so I will not be speaking to the challenges facing your field. My goal here is to provide a review on current standards of today's AI and ML technologies and how fast these capabilities are accelerating. However, I am quite interested in particular use cases. I would welcome any such discussions. Please feel free to email me at the address in the lower left-hand corner of the title slide. With the growth of AI and ML in mind, let's start by defining the three layers: artificial intelligence, AI, machine learning, ML, deep learning, DL. AI, which, as you can see in the diagram, is the most broad concept, stemming from a long-standing thought that machines can do the things that humans currently do. This has been employed in numerous ways over many decades, including everyday tasks such as spam filtering, product recommendation, or next best action recommendations for policymaking. Machine learning, as a subset of AI, came from a practical way of taking large volumes of data and turning them into predictive insights. ML identifies hidden patterns in large volumes of data and then uses those patterns to assess what will happen in the future, why that event is likely. Machine learning applies more specialized algorithms to develop specialized outputs across breadths and depths that a human alone could not simply comprehend. Examples include predicting when a customer is likely to cancel their mobile service or predictive maintenance of device failures. Deep learning, which is a subset of machine learning, is about doing tasks at massive levels of computational power that were previously intractable. Its techniques are more complex and use more advanced algorithms like deep neural nets and processing a broader set of data like images and speech. Such scientific methods are designed to extrapolate important insights from less used data sources. For example, automatically predicting blindness from retinal scans. Today's agenda includes an overview of image and video recognition, video cameras enabled with deep learning, natural language understanding, text, voice, and conversation bots, and fully managed machine learning platforms. Streaming data is ubiquitous and has created the demand for image processing applications to return results in real time. State-of-the-art image recognition APIs allow us to capitalize on powerful visual analysis and build more powerful applications to search, verify, organize millions of images, or to extract motion-based context from video stream. Real-time recognition technologies are capable of detecting objects, scenes, faces. They are capable of extracting text, recognizing politicians or figures of similar celebrity, and identifying inappropriate content and images. ML video APIs can track people and detect activities, even if the individual face isn't visible or if the individual exits and re-enters the frame. This makes investigation and real-time monitoring of individuals, like persons of interest, easy and accurate. Example, this could be used in an application that sends a real-time notification when someone delivers a package to your door. Indexing metadata such as objects, activities, scene, and faces in turn make video search easier. Not without irony, the difficulty for deep learning technologies is in high scalability, and high scalability is a most necessary requirement for real-world use. We can see each label object or scene is returned with a confidence probability. Facial analysis has thousands of labels. One moment. I'd like to realign my slides. Facial analysis has thousands of labels. We can see age range, gender, demographics, but it also reaches low-level tagging, such as has mustache, and again is returned with assigned probabilities. Facial analysis can also provide sentiment capture and can compare human faces. One of the most common use cases of recognition is image moderation. Is image moderation. For example, easy filtering of videos for explicit and suggestive content. Other common use cases include face-based user verification, license plate registration, immediate response for public security, investigative analysis of events for public safety, searchable image library, or index for video archives. Had time been more permitting, I can either revisit some very interesting demos. One is more formal. It demonstrates how recognition technology can power an enterprise retail like Amazon Go, down to how within half an hour I could spin up a small demo using like webcam remote detection for labeling. Speaking to the acceleration pace of AI and ML technologies, new potentials are sure to be realized this year with the introduction of the world's first deep learning-enabled video camera. A deep learning video camera uses deep convolution neural networks to analyze visual imagery. What is more novel is that the device itself is a developmental environment to build computer vision applications. Models that have been deployed to the device can run without being connected to the internet. Inference can be performed locally. The DL video device can communicate with other ML endpoints. Taking the AWS Deep Lens, for example, or any equivalent, it can talk with a corresponding ML platform, which enables model training and validation. It can communicate with any Lambda function platform, which would mean given a detected event, it can trigger an automated action and, for example, run inference against CNN models. Lastly, it can also connect to an IoT application platform, which could message, data cache, sync, and perform ML inference capabilities with other connected devices. Come April, I anticipate we will see very imaginative ways developers will exploit DL camera devices. Natural language understanding is key in applications such as news gathering, text categorization, voice activation, archiving, and large-scale content analysis. NLP-driven technologies attempt to analyze, understand, and derive meaning from textual information in a smart and useful way. The most common use cases include voice of customer analytics, where one can gauge whether customer sentiment is positive, neutral, negative, or mixed based on the feedback received via support calls, emails, social media, etc. Semantic search, which is enabling a search engine to index key phrases, entities, and sentiments. and provide a better search experience. I took the body of an ITU news article. 4 out of 5 people in less developed countries can access mobile networks but are not using internet. I passed this article, the body of the article, through an NLU understanding API. The NLU was able to extract entities such as ITU being an organization, 2016 being a date. NLU could also provide key phrase extractions. This is properly used by many businesses to provide automated keywords into Google's, for example, Google's search engine to maximize its search hits on most relevant to their content. And lastly, NLU can offer sentiment modeling. A prominent use case is comment moderation in public forums and online newspapers. Lifelike speech is an increasingly important feature of hands-free device communication. As always, low latency is a steadfast criterion. G2P refers to grapheme to phoneme conversion. The conversion of a letter grouping to speech sounds. It is the process of using rules to generate a pronunciation for a word. Rules are created by an automated statistical analysis of a pronunciation dictionary. Lifelike speech technologies rely on lexicons. Lexicons are often industry-specific and typically proprietary. For example, a human may use the abbreviation DFI, but an automotive lexicon would convert this to direct fuel injection. Speech synthetic markup language denotes where lexicon rules are enforced over the default. You can see this in the middle column. This technology is commercially used in 50 voices supporting 30 languages. However, it should be noted that high-quality sophistication has been made farther progress in European languages than anywhere else. Conversational interfaces.
Sorry to interrupt,
Yes.
Ms. Elena. Can you begin the wrapping up? Because we have one more speaker here.
Certainly.
So, right.
I think I would.
Yeah, make it 5 or 10 minutes.
Lovely.
5 minutes.
I have 2 more
Is it
slides.
possible?
It should not be a problem.
Okay.
Thank you. I will just say that building conversational interfaces requires high-quality voice and text images, typically driven by automated speech recognition and natural language understanding. ASR and NLU are progressively making chatbots more sophisticated and natural sounding. Use cases include information bots, where automated customer support agents and bots can answer questions. Application bots, where a standalone pizza ordering agent or travel bot. Enterprise productivity bots, where you can build a custom bot to connect enterprise data resources. Or an NLU bot to control issue commands to connected devices. The introduction of machine learning platforms that are fully managed has resulted in the democratization of ML tools. The entry barrier to using ML algorithmic approaches has been lowered. A fully managed machine learning algorithm platform should include the most common ML algorithms like exploratory data analysis, clustering, image recognition, built-in A/B testing, and so on. Therefore, the developer's focus can be on his or her application, and progress is not prohibited. Data scientists spend around 80% of their time on preparing and managing data for analysis. Hence, only 20% of their time is used to derive insights. Only 28% of companies indicate that they are currently generating strategic value from their data. If I take Amazon as a company, for example, our .com engine is driven by AI/ML. The paths to optimize robotic picking routes in our fulfillment centers are driven by AI/ML. And our supply chain forecasting, capacity planning are all informed by AI decisions. Our drone initiatives, computer vision techniques, use case by use case, AI/ML is simply becoming embedded in our heritage. Many thank yous.
Have any questions? Yeah, we got one question.
Hi, this is Jacob Heulis from Nokia. I just have a question. Do you offer anything related to real-time inference? Because in telecommunications, you often need to make inference with very hard latency constraints. And do you have the option to leverage, for example, FPGAs in your data center to speed up inference?
I'm not an expert in that area, but I would say that we have some capabilities there. I can only speak for AWS products and services. That's where my background is. But are you familiar with Kinesis Stream? And I think you can run Kinesis Stream on FPGA instances that can address this.
Okay. Thank you. I'm not.
Or please feel free to email me if you want to have a longer discussion. Thank you.
Okay, thank you.
Yes. Thank you for your presentation. Thank you. Our next and last speaker is Mr. Altaf Shaikh. His topic is machine learning for 5G SON. Go ahead.
Hi everybody. My name is Altaf Sheikh and I'm doing my PhD at TU Berlin. I'm also affiliated with Telecom Innovation Labs in Berlin. I won't take much time. I would like wind it up in 10 minutes. So I'd be talking about self-organizing networks in 5G. I think from the morning we have been hearing this term self-organizing network like many times. I think I don't have to give any introduction for this. So it's, if we look back, so it's already like 10 years since self-organizing networks was introduced. It was first introduced with the release LTE release 8, and then later on with the further releases it was evolved. So meanwhile, several vendors have okay, some parts of the self-organizing network was standardized by 3GPP, and the way how to implement certain algorithms was left for free. Right, there's full freedom for vendors to actually implement different solutions. So in the market, we see like several vendors, so obviously several solutions. And the main purpose of self-organizing networks was to reduce expenses and also have automated network planning, configuring, and installation, and lots of use cases which are very beneficial for the operators. And we see that it's also very important for 5G to have self-organizing networks from the beginning itself, from there, or to deploy. These are some of the functions which are very the first defined functions, but what we see is like most of the function, only a few of these functions are actually deployed by the operators. So if you ask me like how much, it's just 30% or even less than that, because for example, the function automatic neighbor relation, which allows the cells to be automatically added to neighbor lists, and then this is something very beneficial for the operators, so they actually deployed this very widely. And coming with the other features, other use cases such as PCI optimization or mobility robustness optimization, actually didn't find any operators trying to deploy these settings. Or okay, for example, there are algorithms, but operators sometimes maybe don't activate them, or they're not actively using them. So there are reasons why operators are not using. Maybe operators are not really ready to have a complete automated network. Plus, there are different design weaknesses that we identified in a self-organizing network algorithms. So, for example, there is, if you take one function, one use case called PCI optimization. The basic purpose of this use case was if there is an adjacent base station or a neighboring base station which use the same cell ID, the one who detects this should actually restart itself. So the approach of this is like so simple. So if you observe that restarting a base station is based on a parameter which is called cell ID, which is broadcast in nature. So everybody who has access to the interface can actually look at the cell ID. So I'll come more why I'm telling this in the next slides. In the next slides, also some decision making approach in self-organizing networks is not really efficient, and the algorithms are not really bulletproof, and then there could be lack of trust to give automation to a software, or handling the complete control to a software is not maybe what operators require. Or so we really looked into some problems in the design of SON at our research. So for us, the major goal is like looking at security in mobile networks, or particularly on the air interface. So when I see at a mobile network, I actually visualize it this way. So there are mobile phones, there are base stations, real base stations, and along with that, there are rogue base stations also. And we have learned so much that the SON, or the network automation, usually happens with the data that's collected from, let it be phones, or let it be base stations, or over the air interface. So there is lots of SON data that's collected from these devices, and these devices are really in a vulnerable location. So there are chances that a rogue base station is being operated close to a real one, and a rogue base station has the capability to actually use these phones and inject false information into the network. Since this rogue base station can actually act as, or impersonate completely a real inode B by spoofing, or by using its cell ID or physical, because these are the parameters, like the broadcast parameters, that actually identify a base station. Those are available for an attacker, or for example, an active attacker who is operating a rogue inode B. So he can try to set up a rogue hotspot or rogue inode B and try to induce phones to actually send false information into the network. Like when I mean information, it's mostly measurement information, also certain kind of radio link failure information, or handover failure informations, or this type of information is really used for optimization by the SON algorithms. For example, if we take one case, let's say there are there's a real base station and there is a rogue base station. So by operating with the same cell ID, it can actually cause handover failures, which means that, for example, let's say somebody is operating a rogue hotspot for a minute. It can actually cause a damage of 50 to 60 dropped calls. So which is not nice for the operator, which is also not nice for the subscriber. So the reason is the content or the information in these reports is not verified either by the phone nor by the network. So the information received is blindly trusted for different optimization purposes. For example, like I said, since so many handover failures happened, so these will be actually registered against the real base station, but the one who causes this is a rogue base station, and the network has no idea to distinguish whether the root cause of this actually. So by the time they realize that, okay, by the time they find the root cause, lots of damage might have happened already. So we were talking about lots of data from the morning. So I think we also need like machine learning solutions, not only to detect faults or like this, but to also check the accuracy of the data, or to verify whether the information that's received by the network is true information or a fake information. Actually, I could expand a lot because we found several weaknesses in different functions, use cases defined, and since these are like problems with the standards, we approached GSMA and we also approached 2 other operators trying to discuss more the security aspects of these issues. And currently these are in actually progress, and the operators actually agreed with us that, okay, possibly if there is somebody operating a rogue one inside a self-organized network, there are chances that it causes lots of damage. So we believe that we need solutions. So, for example, first obviously solution could come like changing the standards, and changing LTE standards is not an easy task because there are already lots of deployments happened, and yeah, if a change takes place, it brings a lot of compatibility issues, also power draining issues, and lots of efficiency problems. But I think there is something called public key based authentication that's coming up in 5G, but it's not a mandatory thing to implement. So there are still chance of rogue base stations to be seen in 5G. The second option could be like adding intelligence to the self-organizing network. Verify the data inside the network, either having intelligence exactly at the E node B or also at the OAM, or following a hybrid approach and trying to learn different patterns or different successful patterns and trying to filter the unsuccessful patterns. And yeah, several approaches could be adopted. Like somebody pointed out before, lack of real data, it really hinders the research of doing machine learning in self-organizing networks. So because it could be done in simulations, but that's not real gain. So I think it's really essential to have access to more data that usually operators have. Just want to conclude with a new project, something like SelfNet. It's a 5G PPP project. So that's more concerned about self-organizing capabilities in 5G networks. So they try to bring up something called self-protection, but this is actually protection from signaling floods, which does not solve all the attacks or all the problems that we mentioned that I mentioned in this presentation. So still there are lots of problems that need to be handled to actually verify the data that's coming from air interface. Yeah, that's the end of the presentation, and I thank ITU for this opportunity.
Yeah, go ahead.
Thank you. I actually have a question which is inspired by this point about security. IoT is one area which is probably the big driver for future networks, and we talk a lot in IoT vertical about privacy of data. In this workshop, I mean, we can look to more about focus group or objective. But in this workshop, I've not yet heard about privacy in general. And my question is this because now the business model we are looking at in this context are quite limited? So all this data is for one operator. But when we talk about how to optimize the space data, we may decide to remove data which are privacy data, location information or other context information may be private. So my question is it a question that is addressed, for example, from the scientific point of view, the privacy in terms of machine learning for networks? Because for IoT, it's already hot, or is it just not addressed now because it's not so urgent? Thank you.
So the question is why security is not in the focus.
Privacy of data.
Okay. So I learned that we have to use personal information, right?
So identify information.
No, I mean this is not on purpose. We want to, in fact, I mean, this is an important topic, also in the context of machine learning. And it would be nice to have a working group in the focus group focusing on privacy or personal information. And so privacy preserving machine learning is a hot topic in research, as far as I know. But there's a contradiction for me. What is the contradiction? I mean, we had a lot of talks about interpretability, reliability, okay, trust. do we trust? I mean, the question is how long should I train the machine to trust it, and so on. So there is a gap. In fact, we train and the machine does something, and then we hope that the machine does the right thing. But if you talk to security guys, I don't know a single one who would accept something like this. I mean, security is about just also proofs. You have to prove that the system is secure. It's not just like we hope it will secure. So for example, there is a big research gap. You have a data, right? And data includes some personal information or information you are not willing to provide to third persons, right? And then you would like to do machine learning using this data. And then you have information available in the internet. Okay, so now the question is, I would like to anonymize the data, so to process the data, okay, to remove, this personal information. Maybe I can do it, given the information available in the internet, right? So there is some kind, not now, but also in future, no? So now the question is, if I remove the personal information, there is something useful in the data. I mean, what has been remained, no? I can do machine learning using this data. I mean, so you remove something. I mean, you want to protect, and something will be left. You will have something, but I don't know whether it is still useful to do some machine learning. So what I want to say is that in principle, security and machine learning it's highly relevant, but to be honest, I think that we don't understand many things. And then if we talk to security guys, I cannot imagine they would accept, the approach like, we train something and then hope that, it will work. Okay, so this is just maybe comment on this.
Yeah, it's the very beginning of the focus group, so it's open to all kind of subject except ethics. Yeah, gentlemen.
Thank you, Mr. Chairman. My question is on rogue station. This rogue station, did you dictate it, or are you postulating it? If you dictated it, was there any strategy of locating its source? Is my question clear?
You mean if there is a chance for the operators to locate it?
The question is, have you had cases you have identified? If you have had cases about rogue station, how did you dictate it, and what effort are you making to dictate it? Because it will help in the analysis we are projecting. Thank you.
There were several cases where maybe instead of rogue stations, the often used word is IMSI catchers. So which were detected quite many times here and there, also in Norway, several times in Germany. But if you ask like how to dictate them, you mean I dictate, or somebody who is trying to install that, they try to dictate it or operate it. So there could be like lots of purpose of using this kind of rogue stations. It could be doing a direct denial of DOS attacks, or it could be something related to privacy or trying to track somebody. So there are lots of use cases even this kind of devices have. So it's very common to find such devices. It's just like internet. I mean, mobile communications is not any different. So I see it just like the internet.
Okay, one last question.
Thank you. I have a question from Samuel E. Digu. How do you handle the lack of real data And do you have access to real data from mobile operators?
Actually, no. But all the analysis we made till now was based on certain documents available from different vendors. So we try to read their documents, try to make analysis how their algorithms behave, and based on that we make a study. But I think it's a good approach. But we are trying to approach now different operators. But anyway, we approach GSMA, so they are trying to check with different operators.
Thank you.
Okay, thank you, Ataf. And I think this wraps up this session, and I'd like to listen the last comments from Chairman.
Okay. Also, thank you from my side. I think, I mean, in my view, this was a really interesting workshop. I learned a lot, and also maybe just I would like to say some words. Okay, what is the outcome of this workshop? And first of all, we took some notes, and then you know, also some slides are available, so everybody can access. But as far as I know, not all the slides. No? But anyway, I mean, we took notes from some topics, and then for the focus for the meeting of the focus group, I mean, we have contributions, but I will try to extend these contributions, you know, using the talks presented today. So I think that there were some interesting aspects, and we can, you know, take over during the meeting and then use it as an input to establish working groups. And so this is more or less, I think that this was the original idea of this workshop. Tomorrow we have, you know, the first meeting of the focus group, and so the idea was to organize the workshop to see, you know, I mean, what are the problems we have here. You know, we had interesting talks from the industry and also from different players, and so network operators, network vendors. And then based on this input and contributions we received, you know, to this meeting of the focus group, we will try to establish, you know, working groups on specific topics. I don't know how many, because I learned that, you know, here everything should be achieved by consensus, and it's not so easy to achieve consensus. But I think maybe 4 or 5 working groups, you know, focusing on some specific topics of interest. So I mean, on the other hand, we need, you know, enough interest. You know, it doesn't make sense to establish working group, you know, with 1 person or 2 persons. So we just need enough meat, right? So this would be, you know, this is the main outcome. This was the main idea for this workshop. And from my side, I have to say that it was a very good workshop, and I learned a lot. And we will use this input, you know, tomorrow and, you know, in the next 3 days. Okay, thank you very much for attending this, and yeah. That's it, no? Thanks.